Okay, so can you hear me now? Yes. So we started with the problem last time that we have 6 observations of people with weight and systolic blood pressure, and we wanted to predict from that set of observation what will be the systolic blood pressure of another person who has a weight of 49.9 kg or something, right? So that is the prediction. We also said that we can develop an equation based on the observation, and that equation will help us to predict the blood pressure of a new person, whatever may be the weight of the person. And to develop that equation, you can do it mentally, which you did, which was, if you remember, 10 plus 2x, right? 2x is the body weight of the individual, right? And so you put any person's body weight in x and you get the systolic blood pressure. So to do prediction in clinical medicine, we use the same strategy, which means we first have a set of observations. Based on that observation, which we feed to statistical package like SPSS, SPSS helps us to build that equation because our data is very complex, so many variables, we can't do it mentally, so we leave it to SPSS to do it. And SPSS does exactly the same thing as you do mentally, right? You have seen that. But SPSS spews out so many, you can say outputs, which you need to be able to understand and use appropriately. So to that extent, you have seen that in exercise 2, when we had 12 set of people, and to make it slide so it will be better. Is it better seen now? Yeah, so we had 12 set of people, 40, 50, 60, 70, 80, 90 kg in pairs, and we had their blood pressure, which was very similar. In which case, we could draw a scatter plot. Scatter plot is a plot of x-axis and y-axis. Y-axis usually keeps dependent variable and x-axis has dependent variable, independent variable. And then you will see where the points lie. And then you developed, you found that all fall in the same straight line. One thing which I want you to do is to find out what is the average systolic blood pressure. So if you add 90, 110, 130, 150, 170, 190, how much does it come to? And divide it by 6. So you will get the average of 6. If you do it for 12, how much does it come to? So while you are doing it, I can use statistics and do it quickly, maybe. See whether you can do it by calculator faster or we can do it by using SPSS. So see, the mean of systolic blood pressure is 145. Was it from this? I did it from, no, I did it from exercise 3. Sorry about that. I have to do it from exercise 2. So that will be, I think, not this, not this. I think I need to add only one of these. So mean is 140. Right? 12 observations, minimum 90, maximum 190, mean is 140. Everybody could follow this? You do it at home, you will find the same answer, right? So 140 is the mean. Now I want you to see how much is the deviation from the mean for each of these individuals. So first one is deviating how much? 50. So somebody can make a note of that, 50. Second one is deviating by 30. And third one by 10. Right. Fourth one again by 10. But here I'm taking without the sign. We will minus 10. You can write minus 10, no problem. But what is the way to get rid of minus? Square it. So we'll square all of this. Just first note the number 10, then 30, then 50, and again it repeats itself, right? So if you do the square of this and add it up, how much it will come to? 50 into 50, 2500. 2500, here it will be 30 into 30, 900. So you keep writing, someone keep writing. 2500, then 900, then this one will be 100. Can you add it? And just double it, right? So how much it is coming to? Sorry? 7,000. You see the same observations are repeated again. So it will be 14,000, right? So I don't need it perhaps. So let us see, you have calculated by your pen and pencil. Let us see whether SPSS does this. It does it, and it does it in the regression also. You can do it otherwise also. And we had used SBP1 and weight 1 as independent variable. Remember, do you remember whether if you draw a line, how many of these values will fall on the line? Don't remember? All, that's right, that's right. If you don't believe me, I will show it to you. So do you see 14,000 anywhere? It comes under the table called ANOVA, right? ANOVA stands for Analysis of Variance. So variance is nothing but what you are doing now. So 14,000 is the sum of squares. We shouldn't call it variance. Variance is after you divide it by the number, means take out average of sum of squares. So sum of squares, which you did just now, comes to 14,000. Now all of this is under the heading regression, because all the lines fall on the same line, right? All the points fall on the same line, which means regression line is capturing all the points. No point is lying outside the line. So all the sum of squares is here in as 14,000. Now let us see, if you take example 3, where do you remember whether all the points were falling on the line or not? Anybody remembers? None of the points were falling on the line. But there was a line, and we will show it to you. If you want to see this one, you can put a graph. regression variable plot. And that is example 3, weight 2 and SBP2. If you don't remember, this is how the plot looked like. I hope I have to remove some options because that square thing I want to remove. These bin points will take it out. Yes. Can you see this? None of the points are on the line. I made a mistake did anybody notice what is the mistake? Weight should be in the right. Now you can see. So this is the line we got. Now, how much is the distance of the points from the line? Anybody remembers? The line has been drawn along the average of the two figures, right? You remember that? Because if you remember, our equation was 15 plus 2x, right? So none of the weights were actually correctly predicted. There was an error of 5. Error of 5. You don't remember, then I have to show it to you. Regression, linear. We want to use SBP2. SBP2 is the dependent. And weight 2 is the independent. So 15 was the constant and 2 into weight. So 15 plus 2 into 40 will give you 95 from the, and this is called deviation. So they are 5 deviated from the line. Each of the points, because that is in the average, so they are 5 points distant from the line. So now let us take difference and square. If 5 is the difference from the line and this point, then what is the square of this? 25. 5 is the distance of the second point, lower point also from the line. The square is 25. So 25 plus 25, 50 plus 25, 75 plus 100. So actually 25 plus 25 repeats 6 times, no? No, 300. 25 plus 25 is 50. 50 into 6 times, no? So 300. Do you get it? So it is not 150. 25 plus 25, 50 into 6, 300. And you see, that is what is the residual here, 300. Right? So what is residual? Residual is the deviation of the points from the line, but because there are some positive, some negative, you square it, then you get everything plus. So you add it up, that is what it is. So this is how you can interpret. If all the lines are on all the points are on the line, then your residual is 0, which means all points can be very well explained by the regression line. If you find points away from the line, then you have to find out how much, that is the residual. So residual is what is not explained by the line. And if you take 14,000 out of 14,300, so total sum of squares will come as 14,300. But that you can do, it is the same process which we did in example 2. You add it up, it will come 14,300. 14,000 is explained by the line, which you saw earlier. 300 remains to be explained, so that is why 300 is in the residual. Now, in your calculator, can someone do 14,000 divided by 14,300, just to know how many of the points is explained by the regression line? So can you do this? 14,000 divided by 14,300? 0.979. So do you see 979s anywhere? R square is 0.979, right? So if anybody is reporting regression, or when you are reading about this, you have to look at R square. That is why we don't look at ANOVA table, because R square summarizes the ANOVA table. What is R square? R square is the proportion of differences, you can say, or proportion of sum of squares, which is explained by the regression line. The regression line catches 14,000, 3,000 remains to be explained. You are not explaining it. So out of total sum of squares of 14,300, 14,000 is explained by the line. That is what R square is, 0.979, right? So now you have some idea about this, and I hope full idea about this, right? So that is the output you get from SPSS. You can modify it, you can add, you can do a number of things, but this is what you get. So even if you don't look at ANOVA table, nobody reports ANOVA table in their papers, at least R square you should report, because R square gives a fair idea of what the ANOVA table would be like. And similarly, of course, you will report the coefficients, constant, and what is the p-value. These are the things which you have to. Yet we have not understand what is this standardized coefficient. We will go and see whether we can understand this. Right. So you have done this. Now look at this graph. This graph is graph of blood pressure, systolic blood pressure, which is measured in patients who are admitted with stroke in an international stroke analysis, secondary analysis of the data which is published in stroke. What we will see is that when systolic blood pressure is less than 120, then these are proportion dying within 14 days. Least number of deaths, or least percentage of death, is at what blood pressure? Can anybody read and tell me? 140 to 159. So when your friend, or your friend's relatives are admitted and they have stroke, don't insist for getting 120 by 80, right? When there is acute stroke, you see there is pressure is increased inside the head, you need higher blood pressure to push the blood into the brain. So 140 by 159, maybe up to even 170, it is 179, you find least number of deaths. Deaths are by the solid line. As blood pressure increases, the proportion of death increases. As blood pressure decreases, proportion of death decreases because there is not enough pressure head to supply the blood to the parts of the brain, and there may be aggravation of ischemia, enlargement of infarct, and people may die. So, is the relation, yes? Less than 120, so low blood pressure is not good for patients who have acute stroke, right? This is for ischemic stroke, yes. Yes, you are right, ischemic stroke. Now, when we talked about relationship, whether the relationship between independent and dependent variable is linear or not, you must be wondering, is there anything called nonlinear? But what do you think? Is the relationship between baseline systolic blood pressure and mortality is linear or not linear? Not linear. If it was linear, then it will be one trend, either with rising blood pressure or with decreasing blood, it will be one trend. In this case, you find almost U-shaped curve, right? This is why don't use linear regression in this. You should know when to use linear regression. You should also know when not to use linear regression, right? So this was just an example. I thought I will just show it to you. I showed this to you. Is there linear relationship? No, there is no relationship in fact. So don't use, but SPSS doesn't know it. If you press the button, it will give you output. So before you press the button, you do a scatter plot, check it, whether there is linear relationship or not. And I told you, you can check it by statistics, you can check it with your eyeball, and then only use it. So we have, just to remind you, we said regression equation predicts the average value of dependent variable. Remember, not 90, not 100, but 95. From scatter plot, you have to check the scatter plot. And then looking what? Looking at? Yes, simply seeing that is also enough. But if somebody is not sure, you can use statistical test. So we have already covered this. There is some error in every predicted value of dependent variable for a given value of independent variable. And error is the extent to which predicted value differs from the corrected value. We also said how the best fitting line is based on least square method. We have already said that. So least squared method is the way linear regression is usually prepared. Now let us go to exercise 3, which is, I give you information, one more information about that observation, that is weight and systolic blood pressure. There was one more observation which I didn't tell you, and that is about sex of individuals. Sex is a term used in biology, gender is a term used in sociology. Remember this, right? Some Canadian expert told me when I hesitated to use the word sex, he said, no, you are talking about biology, use the word sex. Right? So, sex of individuals was not told to you, it is given in this last column, and coding has been done. And the coding is, for females it is 0, and for males it is 1, right? So somebody told me, sir, can you reverse the coding? I said, why? It doesn't sound good. 1 in decimal is 100%, and 0 is 0, right? So don't say females are 0 and males are 100%. I said, this is not meant to tell anything about the capability. It is just a indicator variable. So just take it as indicator variables. Sex is 0 means females, 1 means male. And you remember, I told you that 40 to 90, 50 to 110 was not followed here. 40 to 100 and 50 to 120. So last 6 observations had very different systolic blood pressure than first 6 observations, isn't it? So now I will see who is good in mathematics. Can you form an equation where we can predict the systolic blood pressure by using weight and sex as independent variables? You said 20 plus? Okay. Remember, you have to use two terms on the right hand side, right? Systolic blood pressure equal to, so you said about males, I want one equation which will give value for both. This is why coding has been done. Coding has been done with a purpose, and coding has been done with some design. So if you can find the equation, tell me. Sorry? 10 plus 2 that is for, but come to the next. Here it is 100. And you have to have two terms, right? Also use sex on the right hand side, right? So that both the terms are represented. Then only your equation will be right. It will not be right with one term. Yes. Correct. Can you write it? This is right. If I had a blackboard, I would have said, you write it, then we will check it. Can you write it? There is some ink there. Yeah. Don't worry about camera, should not worry about that. Let her write it there so that everybody can check whether it is fitting the bill or not. Sorry, this in research methods, yes. That's why I said those who have attended, the systolic blood pressure is equal to so read it again, please. 10 plus twice weight into 10 into sex. Now you see, what happens in the upper 6 observations is 10 into sex is 0 in this case. So this is 0. Therefore, the formula becomes weight, systolic blood pressure is equal to 10 plus twice the weight, isn't it? Right? That is what I think Dr. Dung you said. That is for the upper observations, it is right. So you have to make the second term 0, which becomes 0 if you say 10 into sex. The lower 6 observations will add 10 to it because for them the coding of sex is 1, right? So it will become 10 will be added every time. Did you get it? Now we have to see whether SPSS can do it the same way or not. So I have added under 222, we have weight, same systolic blood pressure. So 40 is 90 here, 40 is 100 here, and there is coding for sex here. So let's now see whether SPSS does the same thing. Linear regression. So one more variable I have to put, which is this, and now just press the button. Now see, constant is 10 plus weight into 2, this is what you said, weight into 2, plus 10 into sex, right? That is what it is. So what you have done, SPSS does the same thing. Okay? And now we have explained everything. Now we explain the variation. So what is the residual now? Residual here has become 0 because you have found a variable which explains the differences. Now nothing remains to be explained. Now everything is deterministic, which means you can determine exactly how much is the systolic blood pressure if you know the weight of the individual and sex of the individual. This is why residual is 0 now, and obviously R square will be 1 because you have explained 100% now. So this is now 2 variables are there. So what have we learned from this? 2 independent variables now, right? What are those 2 independent variables? Weight and sex. What is the dependent variable? Systolic blood pressure. So now we have a linear equation that has 1 dependent variable or more than 1 independent variable. It is called multiple linear regression. Right? What is the term we used for the only 1 variable, 1 independent variable, 1 dependent variable? Simple linear regression. So it is multiple linear regression. Now this regression is also called multivariable analysis. Right? And then we will come to, depending on the nature of dependent variable, there can be another regression which is called logistic regression or Cox regression. Now, if you remember my first slide, I said outcome data can be measured either in numbers, which is like HbA1c, like blood pressure, like cholesterol. If you are using statin, want to see what happens by using statin, cholesterol is the dependent variable. If you are controlling diabetes, giving metformin, want to see how good the diabetes is controlled, you check HbA1c, that is a continuous variable. It is called continuous because numbers can be 5.2, 5.5, 5.15, whatever it is, right? So this is continuous. What are the other types of variable we talked about? Outcome variables. One was continuous. Anybody remembers anything else? Binary or dichotomous or 2 category variables. So it is a categorical variable, right? It is categorical variable, 2 categories, then we call it binary or dichotomous. Both are synonymous. So that is also a type of outcome variable. That is also a type of dependent variable, right? And then third type of outcome data which we said, I think I have to show my slide to you, you have forgotten. That was time to event, right? Time to event was another one, like time to birth, time to remission. We were giving example of something different, that was time to coming out of ventilator. That was a COVID example, no? Time to come out of ventilator. So this is different type of outcome variable, which is called time to event. So when it all depends on the dependent variable. If dependent variable is continuous, then regression which you use is called multiple linear regression. If there are multiple independent variables. If your outcome variable is dichotomous or 2 category, then an independent can be continuous or dichotomous, doesn't matter. Dependent variable is dichotomous, then it will be called logistic regression. If the dependent variable is time to event, means it is time, right? Time to event, then it will be called Cox regression. That is what the difference is. All have the same mechanics inside. What do? All have one, let's say, one dependent variable and multiple independent variables. They try to fit an equation. That equation, of course, through iteration, Spss does it, it gives you an output. And the output can be written in the form of equation. whatever is your dependent variable equal to some constant, sometimes you may not want constant, plus one variable into this, second variable into this, and so on. So that is another thing which I thought you should know, that if you know one regression, you can basically understand the underlying mechanics of all the regressions. All the regressions behind the scene, inside the black box, do similar things, but depends on the type of dependent variable. Continuous means linear regression, simple or multiple. Binary means logistic regression. And if there is time to event outcome, then it is called Cox regression. Okay? So don't be afraid now. I am sure so far, if you had not got this idea, when you were reading this Cox regression, logistic regression, you just ignored those terminology. But don't ignore it anymore, right? Then we will do exercise 4 now. That is to tell you what are standardized coefficients, right? Remember, we measured weight in kilograms, right? But do you know any country of the world where they still use weight in pounds? Britain has changed to kilogram, I think. But United States still measures, yeah, USA still measures weight in pounds. So if you read their, usual blogs and other things, they will talk of pounds, they will talk of miles. They don't talk of kilometers, right? They talk of miles. So some of you must have seen that. So what would have happened? You must wonder that if weight was measured in pounds, then what would have happened? To do this, let us convert kilogram into pound. Okay? So anybody knows how to convert? You mean pound is kilogram to pound. You divide or multiply? Multiply. So I have already 40 multiplied by 2 into 2 will be how much? 88. So I have already done it for you. Right? So this is weight in pounds. Okay? And you already have systolic blood pressure. So let us see what happens if we measure weight in pounds. So we will not use this weight variable. We will use weight in pounds. Rest we will keep the same. See what happens. What has changed? R square doesn't change, it remains 1. Sum of a squares doesn't change, it remains 14,300, residual doesn't change, it remains 0. What has changed? Constant doesn't change. So the coefficient has changed, 0.909. What was the number here earlier? 2. It was 2. So coefficient has changed. And I have never checked it, but if you divide 2 by 2.2, how much does it come to? 0.9. Is it coming? You have checked or without checking yourself? So actually it has changed the coefficient, no? Isn't it a cause of worry? Worry is, it all depends on the unit. What the regression coefficient will be depends on the unit. So, if we wanted to know which variable is important, you can't do it by this way. Because if, according to you, 2 is an important variable, let's say, you change the unit and it changes. Therefore, it is sensitive to which unit you are in. That is the problem with the usual unstandardized coefficient. But standardized coefficient doesn't change. It is, you find 0.989 here, Now let's go to the other regression equation. This was you see the variable here weight unstandardized coefficient was 2, but the standardized coefficient is 0.989. So standardized coefficient doesn't change even if you change the unit, right? That is the beauty of standardized coefficient. So many people say, though it is controversial, that if you want to know the importance of a variable, then look at the standardized coefficient. That is not sensitive to unit. So one thing which is important is interpretation of the coefficient. So when let's go and spend little time on that. Yeah, let's look at only one independent variable and one dependent variable. Dependent variable is weight, systolic blood pressure. Independent variable is weight. So coefficient you got was 2. What does it mean? Can you think of it? If you have to tell it to someone, what does this 2 mean? That, sorry? Right. But how will you get number 2? If you change weight by 1 kg, then how much will be change in systolic blood pressure? You remember, if you leave out the constant, 40 is the weight, 90 is the systolic blood pressure. So if you leave out constant which is 10, then question is, for 1 kg increase in weight, how much is the systolic blood pressure changing? 2, right? So 1 kg increase in weight leads to 2 millimeter increase in systolic blood pressure. So that is the interpretation of coefficient. For 1 unit change in independent variable, how much is the change in dependent variable, right? Is it clear? So units will remain the same. Systolic blood pressure will be measured in millimeter mercury. This will be measured in kilogram. But for each kilogram increase in weight, there will be 2 millimeter mercury rise in systolic blood pressure, right? That is what it means. That is what the meaning of this thing is. Now, when we do a standardized coefficient, means weight in pound, then what is it telling us? For each pound increase in weight, there is 0.909 millimeter mercury rise in systolic blood pressure, right? So this is easily interpretable, right? This is not interpretable that way. That is why that is the disadvantage of standardized coefficient. But one thing you have seen, standardized coefficient does not change. The question will be, how does SPSS get a standardized coefficient, right? So if those who know that to get rid of unit, you have to do something, right? So what does it do? Like it expresses the weight or systolic blood pressure in terms of standard deviation. How many standard deviation increase is there? For each unit standard deviation increase in weight. So everything is now changed into, unit is changed into standard deviation. Sometimes we do that in our normal life also, like people who have been trained long time ago, they still measure length in feet and inch and yards and things like that, right? But the newcomers or the youngsters, they only know feet, the meters, square meter, etc. So if you want to convert into similar units, you divide each one by standard deviation, then it becomes what is called unitless. But then you have to think in terms of standard deviation, right? That is the problem. But just to check where does 5.9.9 comes from, what you can do is you can find out the standard deviation of systolic blood pressure, standard deviation of weight, divide each of the figures with that. And I have done it for you already. So you see, standard deviation, weight in pounds, standard deviation, blood pressure, I have already done it. And now if you just do the regression, well, let us see what happens. Then you will find, I'm going to remove this and remove this also. I'm going to use different unit, now already converted into standard deviation units. So there is standard deviation, BP2, standard deviation. Here, I think that will be enough just to illustrate the point. See now, when I did it in standard deviation units, our unstandardized coefficient has become 0.990, right? Actually, there is some rounding error here, otherwise it will also be 0.989. So if you do it standardized variables, then you will get same unstandardized and standardized coefficient. Standard, no, we are talking of standard deviation, right? Standard deviation. Standard error is different. We are not talking about that. So, this is just to illustrate a point, forget about it. Point is, standardized coefficients do not depend on the unit in which the variable is measured, and hence sometimes used to determine the importance of the variable as a predictor. Which predictor is most important? Is it age or sex or blood weight, what it is? If you want to know, use the standardized coefficients. This is what used to be taught. Now there is a little bit of controversy around that, but obviously it is free of units, so relative importance you can certainly assess to some extent. Unstandardized coefficients depend on the unit, therefore you cannot tell us the importance of the variable as a predictor. However, if regression is done with standardized values of the variable, then both coefficients will be the same. Have you seen that? Now nobody does with the standardized variables, so don't worry about it. Just to show what does that mean. This is why I brought it here. Now, other things which we need to know is what is the purpose of regression. One thing you know, prediction, I told you. What are the steps of model building? Now, this equation which we make, I don't know why the statistician call it a model. When I was not exposed to research methods and statistics, model meant only one thing for me, right? And modeling also meant only one thing, which you know none of us are really expert in. But when I started hearing model and modeling by statistician, it means making equation, right? So model building means building that equation. Which variable will you choose? How will you choose the variable? Which variable will go there? And then that is what is called variable selection method. We have also not talked about if you want to use regression. And this is what I wanted to tell the guides, that in your own department, there is tons of data where you can use regression and at least determine predictors for whatever outcome is important for you. It may not be first time done in the world, but you can do your own and publish it. You will find some new predictor because your people are not the same as people sitting in London or New York. They are Adivasis, they are mostly tribal people, they have different lifestyle, they have different genetics. So you will find different predictors. I am 100% sure. So you can find out one new risk factor, new predictor of mortality, new predictor of outcome. That becomes a new finding. So people think, how can we do new thing every time? New thing doesn't mean you have to get Nobel Prize. In your population, if you find a new variable, that becomes a new finding. So all the patients which you have seen, malaria, Kala-Jar or alcoholic hepatitis, they say is in plenty, dengue patients, your patients, if you have your data, you will find a new predictor which nobody has seen. Therefore, you can publish it, you can validate it, and every record section, if you have a good record section, this is why I was emphasizing when I came that you must have good record section. Then all thesis can be done on your data and with new findings. So the question is how much sample size you need. Now, I'll give you a very simple formula for sample size or regression, which doesn't require any calculation. You can do it mentally. It all depends on how many independent variables you have. In multiple linear regression, for each independent variable, dependent variable is only one. For each independent variable, you need 10 patients. So we had 2 independent variables. We needed 20 patients, right? Now, that may work, that may sometimes not work. It is a ballpark figure, which is a rough calculation. More the better, but I'll give you a reference if reviewers tell you, how did you calculate sample size, how this is not enough. You can say that, look here, this is the reference which I have used, 10 patients per variable, people have worked out, and I have used this ballpark figure. This is how I justify my sample size. So if you have seen 100 patients, then for multiple linear regression, which means continuous outcome variable, not mortality, for HbA1c, for blood pressure, for cholesterol level, for whatever you want to see, you need 100 patients for 10 variables, right? So like that you can increase it. What if it is logistic regression? Because that is what clinicians use. Reference देंगे पहले करो तो आप. So ठीक है, reference देंगे when you are writing the paper. So we first you collect the data. And then we will see. For logistic regression, you can't use this formula. For logistic regression, you have to look at dependent variable. What will be your dependent variable? For example, mortality. So you have to see in your study, mortality proportion is higher or survival proportion is higher? No, we don't know. Depends on the type of patients. If you are looking at patients who come in cardiogenic shock, mortality will be more than the survival, right? So you have to look at the percent of the two categories. Take the smaller category. So let's say if survival is more, mortality hopefully is less. Let's say 30% is mortality, right? So in that case, how will you calculate the sample size? Sample size will be that for each 10 patients, you can have, or you can say you divide the proportion of mortality by 10, right? Which means you have 30% mortality. You have to see 30% you have to calculate in the number. So if you have 100 patients, 30 of which died, you can have 3 variable independent variables. Right? So numbers of patients. Sample size is number, no? It is not percentage. So if you have 200 patients, 60 people die. How many independent variables you can have? 6. So like that, but you wanted to check for 10 variables. Then what is the number of deaths you have to have? For 60 you had, for 30 you had, for 30 patients you could check 3 variables. For 60 patients 6 variables. For you want to check 10 variables, then 100 patients dying, 100 deaths. 100 deaths means if it is, let's say 20% are dying, 5 times more. So you need 500 patients to do logistic regression with 10 variables. Did you get it? Let me repeat. You first find out which number is more. There are 2 categories, survival and death, remission, no remission. So which category is less? Less category, you find out what is the number. Let's say you have 75 people who have died, right? Out of, I don't know how many patients, maybe if it is 20% mortality, out of 350, perhaps 70 people died, right? How many variables you can check? 7 variables. Because 70 people have died, you need 10 people, 10 deaths per variable. So don't go with the idea that always it is 10 deaths per variable. It may be survival is less, in which case it will be the other way, right? So lower side of the 2 outcome has to be taken, and you have to have 10 outcome events per variable. So it is not 10, but 10 outcome events. Whichever event is less frequent. Okay? So that is about the logistic regression. What about Cox regression? Cox regression, you use the formula which I told you in multiple linear regression. 10 patients per variable you want to check. So now, if you really were keen and you had good record section, you could have given thesis to 5 students right tomorrow. That you do on this, you know 5 common diseases, and they will certainly find something new. So, I think this is my last slide. What is the purposes of regression? I think I have told you on day 1. One is prediction, which means we want to know who will die, who will recover, who has the high risk of adverse event. But the second purpose is explanation. Explanation means what is causing the disease, what is causing the recovery, what is causing non-recovery, or what is causing death. So you want to know the cause, not only prediction, but you want to know the cause. You can use regression for that also, but that requires, I told you in the first instance, that it requires a lot of thinking, a lot of knowledge of biology, a lot of justification, why you will include some variable or you will not. Because if you remember, when I asked you, does increase in weight cause increase in systolic blood pressure? Then 2 people said yes, right? Some people said no. And they brought in lifestyle factors. So if lifestyle factors are causing both, then your model is wrong. If you have modeled for explanation or for causation. But if you did for prediction, it is okay. You don't care whether it is causing it or it is a marker or it is a predictor. It may be a marker. That's okay. So explanation is different from prediction. But for both the purposes, you can use it. Next time, I'll tell you the steps. What are the steps in what is called model building, right? Okay, any question? There are a lot of assumptions, underlying assumptions of multiple linear regression. Don't just use it just as linearity is one of them. Linearity means the relationship should be linear between independent and dependent variable is only one of them. But there are many other assumptions which I will cover later. Okay, if no question, then thank you very much. There should be a committee for plagiarism. Here you had the committee.